Have you ever wondered how AI might one day act as a scientist, figuring out the laws of nature on its own? Researchers are now building tools to test exactly that. Today, we're diving into a groundbreaking project called PHYSGYM, a new way to measure how well AI models can reason about physics when given just the right amount of clues. Let's start with the big question. How do AI models really understand the physical world? Most AI systems today are trained on massive amounts of text, including scientific papers and equations. But when it comes to solving real-world physics problems, like calculating how a coin might fly off a table after a push, they often rely on prior knowledge, the assumptions and facts they've been fed. The problem? Current tests don't let researchers control how much prior knowledge an AI has. It's like giving a student a math problem, but randomly hiding parts of the textbook. That's where PHYSGYM steps in. Think of it as a physics lab for AI. It's a simulation platform where AI agents must discover the rules of a system by experimenting, just like human scientists. But here's the twist. Researchers can adjust how much information the AI gets. At the start, the AI might see a full description of the setup, like a coin on a table, with variables like gravity and mass clearly labeled. But as the test progresses, those clues get stripped away. By the end, the AI has to figure everything out from scratch, just like a scientist with no notes. Let's break this down with an example. Imagine a coin sitting on a table's edge. A vertical push is applied, and the AI must determine the minimum speed needed for the coin to fly off. In the first level, the AI sees all the details: the coin's mass, the table's smoothness, even the formula for gravitational acceleration. But in later levels, those details vanish. The coin becomes a uniform disk, gravity is just g, and the variables are anonymized. Now the AI has to experiment, changing inputs, observing outcomes, and building its own understanding of the physics. This isn't just about solving problems, it's about how the AI thinks. Does it rely on memorized formulas, or can it adapt when clues are taken away? PHYSGYM's design lets researchers test this by measuring two key things. 1. How accurate is the AI's hypothesis compared to the real physics equation? 2. How well does it fit the data it collects through experiments? The results are fascinating. When given full prior knowledge, AI models perform almost like human experts. But as clues disappear, their performance drops, revealing how much they depend on pre-existing information. This isn't a flaw, it's a window into how AI learns. By studying these gaps, researchers can build smarter systems that balance what they know with what they need to discover. So why does this matter? Imagine an AI that can design new materials, predict climate changes, or even explore distant planets. But without tools like PHYSGYM, we'd never know if it's truly understanding the science, or just guessing. This benchmark is a step toward AI that thinks like a scientist, curious, adaptive, and hungry for discovery. But here's the next layer. How do we measure efficiency in AI's scientific reasoning? Think of it like a student solving a problem. Iteration efficiency measures how many tries it takes to get the right answer. Sample efficiency checks how many data points the model needs to learn from. Hypothesis efficiency tracks how many wrong equations the AI generates before finding the right one. In experiments, models like Gemini Flash shined in these areas, while Claude 3.7 Sonnet stood out for its ability to learn from tiny datasets. But here's the twist. Sometimes too much prior knowledge can backfire. One model, Claude, performed worse when given more background info, like a student relying too much on textbook answers and missing the actual experiment. Let's look at real-world tests. In one scenario, models only solved problems at the most basic level because they lacked causal reasoning, the ability to connect variables like, if I change this, what happens next? In another test, the names of variables themselves influence the AI's guesses. It's a reminder, even smart machines can be biased by how data is presented. So what does this mean for the future? These tools aren't just crunching numbers, they're reshaping how we approach science. By balancing prior knowledge with exploration, AI could help us solve mysteries from quantum physics to climate change. But as these studies show, the journey isn't perfect. There's still work to do in teaching machines to think flexibly, not just memorize. Next time you hear about AI, remember, it's not just about processing data. It's about discovering the invisible rules that govern our world. And who knows? Maybe the next big scientific breakthrough will be powered by a machine learning to think like a human only faster. Thanks for watching. If you want to dive deeper into how AI tackles physics or explore more mind-bending concepts, hit that subscribe button. Until next time, keep questioning, keep exploring.